The definite integral is a construct we can use to compute the area under a curve, or between a curve and the zero axis. Let's keep in mind that dx and dt are just infinitesimally small delta x's and delta t's. Okay, so beginning with a derivative relationship, velocity is the derivative of position with respect to time. We can take this equation and multiply both sides by dt, a tiny time interval. Let those dt's cancel out and end up with this. Dx equals v dt. This says that if we have some velocity and we allow time to advance forward by some infinitesimal amount, then v times that little advancement in time gives us an infinitesimal displacement. We move a little bit forward or backwards, a little displacement dx, given our velocity v and time change dt. So if we have a velocity versus time graph, and I note a starting time t1 and an ending time t2, we would like to find the area under the velocity graph between those two times, because we know that area represents the displacement of the object between those two times, the delta x from t1 to t2. Okay, we can find the area of a rectangle or of a trapezoid, but if we have a curve like this, we don't have an easy geometric way of doing it. So that's where this calculus idea is going to come in. Let's pick some particular time, say this moment in time right here, t, and imagine dividing up our area into little thin, infinitesimally thin rectangles like this. Let's center this one tall, thin rectangle right there at some particular time t. And I'm going to color in the area of that one thin rectangle, that orange area there. When I say a thin rectangle, I mean infinitesimally thin. Let's let the thickness of that rectangle be equal to dt, some infinitesimally small time interval. Now the height of that rectangle will be equal to the value of our velocity function at this time t. So velocity at time t is the height of our rectangle. And if it's a rectangle, then we know its area is its height times its width here. So let's express that the area, the tiny area of this one thin rectangle here, that tiny area is equal to its height times its width. So velocity times dt. So that area is the velocity at that moment times its thin little width dt, which we've established is equal to the infinitesimal displacement that occurs during that little time interval, dx. So the argument we're going to make here is that if this total gray shaded area is equal to the total displacement, delta x, from t1 to t2, well, that total displacement comes from adding up a whole bunch of these little displacements, dx's. So we can actually imagine dividing up this whole gray area into a bunch of tightly packed, tall, thin rectangles, like skyscrapers all packed together, or tall trees all packed together. And if we can find the areas of all of those thin rectangles, all those little dx's, and add them all up, we'll get the total area, delta x. Now, a key here is that the rectangles be very thin so that the height of them is well approximated by a single value of the velocity. And the thinner they are, the more accurately we can approximate the curvature here. So in fact, to get a perfect estimate of the area, what we want is an infinite number of infinitely thin rectangles. Okay, so that's the project we're undertaking here. We're trying to construct an estimate of this area out of the sum of the areas of an infinite number of infinitely thin rectangles. So the total area, delta x, from time 1 to time 2, can be found by taking the sum, here's our summation notation, that capital sigma, as our time goes from t1 to t2. So note we have our starting time here at the bottom of the symbol, our ending time here at the top of the symbol, and what we're summing up are the areas of all those tall, thin rectangles. Each one rectangle has an area dx. And dx is equal to the length times the width of the rectangle, so v dt. So we're summing up from time 1 to time 2 all the areas, so all the v's times dt's. Now, this is a rather unusual sum because we'll have an infinite number of rectangles, but each one of those areas is infinitely small. So we're summing up an infinite number of infinitely small things. And that's odd enough that it deserves its own symbol. Rather than just saying a sum, we're going to replace this sigma symbol with this stretched out capital S instead. And rather than saying a sum, we're going to say the integral. So the integral means the sum of an infinite number of infinitely small things. So incidentally, the symbol here is a stretched out S because S stands for sum in our summation. And this is the way that an S was written in Europe in the 17th century when the German mathematician Leibniz developed these ideas. Okay, well, it was actually most likely Newton that came up with all of this first, but Leibniz developed the notation that sticks with us today. So this is Leibniz notation, this stretched out S for sum. So here we have our integral. This is our method of computing this area here. So kind of to recap, what we've got is, what we've established is that the change in x, the displacement, from time 1 to time 2, well, that's a delta, it's a change, so it's always equal to the final value of x minus the initial value of x, so x at t2 minus x at t1, and that will be equal to the integral of v dt, which is the infinite sum of these infinitely small areas. And this is what we call the definite integral, this construct right here. Once again, in words, what this expression means is the sum of an infinite number of infinitely thin rectangles, each of height vt and of width dt, starting at t1 and ending at t2. A little bit more terminology here. So t1 and t2, these values we put at the bottom of the integral sign and the top of the integral sign, are known as the limits of integration, our starting point and our ending point. So this is called the lower limit of integration, and this is called the upper limit of integration. The height of the rectangle, kind of the meat of our integral here, in red here, this velocity function, that has a special name. It's called the integrand. So the meat in here, the height of the rectangle, that's our integrand. And then dt, that's the width of our rectangle, and t itself is our independent variable. Okay, so we're going to take this idea of the definite integral for finding area under a curve and combine that with the idea of an antiderivative to develop what is known as the fundamental theorem of calculus.